Alright everyone, welcome back to our lecture series on finite elements. And today the topics will be a rather mathematical deal, so something that's different from what we've done in the last weeks. So today will be all about answering the question, what does a derivative actually mean? So probably you have a meaning and an idea in your head what derivatives are. But today we're going to change all that, and I will give you an introduction on the why of defining a new type of derivatives called the weak derivatives, and of course also on the how. So how can we define weak derivatives and resulting Sobolev spaces? Okay, and now let's look at the outline for today. Firstly, as usual, a motivation. And today we start with an example that leads you from membranes to integrated circuits. That's something quite interesting here. And yeah, so the application shows that we come to the task of forming derivatives for discontinuous functions, so essentially the motivation for the whole topic of defining weak differentiability and those Sobolev spaces. Then the next part, some mathematical preliminaries, and as I have already mentioned, this lecture today will be more mathematical than usual. And even though it might be a little, let's say, tough to understand all the parts, I will still ask you to try to go through it slowly and understand or try to understand all that I'm talking about, because it's really important for the rest of the lecture. So what are those mathematical preliminaries that I'm talking about? First topic is measures. So we all have something in mind when I say the word volume of some shape. And today we're going to put all of this in a mathematical framework, defining the word measure. And then the next part are integrals, and indeed integrals will be the key in defining our new concept for derivatives, which is kind of counterintuitive, but we will see how great this all works out. And then the last part are actually those Sobolev spaces, and they are defined using the Gaussian Theorem and weak derivatives, and then we will see what Sobolev space actually means.
Now let's start with the motivation. Okay, what you see here is a picture of an integrated circuit on a silicon wafer. The things that I will be talking about are not just purely scientific, so this is an actual project that I've been working on earlier in my scientific life, and I will try to explain now in the following minutes what this integrated circuit has to do with partial differential equations. Okay, let's think about for a second what integrated circuits are. So these are the little chips that are in your computers, so the central processing unit of your computer or your phones. So you those things take care of you every single day, essentially. And yeah, if you want to find out how the electricity is flowing on a certain integrated circuit, it can be computed with the first Maxwell equation that you see here. So Maxwell is a famous physicist who has set up 4 partial differential equations describing electro and magnetodynamics. And the first Maxwell equation in particular is helpful here because it essentially models the diffusions or the distribution of electrical charge in a certain domain. And what you have here in this equation is your function phi, which is the electrical potential. You can imagine this to be the quantity that is diffusing in your domain. You have rho, which is on the right hand side of this equation, so the free charge that is coming from outside. Imagine that you are putting electrical charge into your circuit from the outside. And in here, this epsilon, which will be the important part for the considerations in the following, that's the electrical permittivity. So to say it is more or less the capability of your material to transmit electrical charge. So if you if you think about the examples from the previous lectures about heat transfer, then this can be resembled as the heat transfer capability, if only we're talking about electricity instead of heat now. And now what you see there is a partial differential equation reading minus divergence of epsilon times gradient of phi equals rho. And this is only actually a more general version of Poisson's equation, because if you would set epsilon equal 1, then you would have minus divergence of 1 times gradient of phi, and then you can easily do the computation that the divergence of the gradient is actually the Laplacian. So in a sense, this is only a slightly more general diffusion equation, where the diffusivity, in our case this epsilon modeling electrical permittivity, that is non-constant in the domain. Okay, let's look at this a little more in detail. What I've drawn here is the try to make a schematic out of this actual picture of the integrated circuit. So I've tried to capture the whole circuit in a blue, so more or less our domain that we are interested in. Then I've tried to draw those transistors in yellow and those conductor lines in green, and then there is a red line. More precisely, so I think maybe I've convinced you at this point that this kind of resembles the integrated circuit on the left, only in a very, very simple way. And now let's go into detail a little more. So the blue box surrounding the whole stuff is supposed to be our wafer. And the wafer, that's the engineering term for it, is usually made of semiconductor material. That's in the most common cases it's silicon. So that is a material that is almost not capable of transferring electrical energy, but it's not completely incapable of doing this. So that's kind of difficult to say. But what it means in particular is that this epsilon, the electrical permittivity, is very small, but it's not zero. Then you have those transistors. They are made by doping of the silicon. So that's something I won't go into detail here. So you're putting atoms into your silicon wafer, and those atoms cause this to be capable of actually conducting electrical energy. And you're doing that same thing with those conductor lines. They have a very high electrical permittivity, but it's also doped silicon. And then the red line here is something that is commonly used in practical applications. And the reason for this is precisely the fact that the wafer has small electrical permittivity, but it's non-zero. Meaning that our wafer itself, so the ground material of silicon, it can still transfer very low electrical energies sometimes. Meaning that, of course, most of my energy will go through this conductor line that we have put into this wafer here. But now imagine that the red line wouldn't be here, then there would be still a little bit of energy going from this transistor to this one down here. And that's usually something that you don't want, because if you are putting conductor lines between certain parts of your integrated circuit, then usually what you want is that the electricity only goes through those conductor lines. So what's done in practical examples is that you put silicon oxide layers into these wafers, and that's like an actual isolation part. So meaning that if I put the silicon oxide here in the middle, this red line, then this is a part where actually no electricity is flowing through. And that's more or less in order to ensure that the stuff is only going where I want it to go. Now, here comes the interesting part. why do I draw all of this? Well, usually it comes down to an optimization problem that you want to use as little of this silicon oxide as possible, because it's cost efficiency. And still you want to use as much of it as necessary in order to make sure that your circuit is doing what it wants. And to do that, you usually take this type of domain setup and actually try to solve or approximately solve Maxwell's equation on this domain with the respective electrical permittivities, epsilon, in those respective parts. And then you see, okay, well, for example, if I see that there is nothing going on from here to there, then it's completely fine. Then I can drop the isolation part or make it smaller, so I can optimize with this. So what you want to do is you want to solve this equation up here in the domain, but you have to take into account that epsilon has different values here. And here you can already see that this can actually be quite problematic, because in those practical applications you have certain parts that of that integrated circuit that have different values for epsilon, and they have sharp edges in between. So meaning that if you go from out here to a point in here, there is a clear and sharp point where your electrical permittivity changes from the value of almost 0 in the wafer to a value that's definitely bigger than 0 inside of your transistor. Meaning that epsilon, our coefficient function, is discontinuous. And if you see that epsilon is inside of this divergence here, we can already guess that this turns out to be a problem. Because if you apply the product rule on this divergence of epsilon times gradient of phi, then you see that, okay, the first part is minus epsilon Laplacian of phi, so more or less the standard Poisson's equation part. And then you have also, of course, product rule, a gradient of epsilon. And that kind of sucks because, well, it's a derivative of a discontinuous function, which by standard means of derivatives, we simply cannot compute. But still we want to compute it because we need to solve Maxwell's equation on this domain for the integrated circuit in order to, actually know that it works. So you see the dilemma here. We need to do a solution for this problem, but strictly mathematically, we can't do it if you think about the gradient of epsilon as the standard gradient as you have learned about it in your studies before. Now that we've seen in a very applied and practical example that it can be necessary in certain situations to actually compute the derivatives for discontinuous functions, for example, when it comes down to material parameters, which are usually discontinuous, then, what do we do now? Well, in order to actually deal with those derivatives of discontinuous functions, we have to lay some mathematical groundwork, meaning that we have to do a little effort and do some theoretical background work in order to then be actually able to deal with our applied program. And so I would like you to try to follow up what I'm talking about now, and don't be shocked by the more theoretical contents in this case. They are actually necessary, so always keep in mind the problem that I have just explained. Always think about our integrated circuit where you want to model diffusion of electrical charge using discontinuous parameter functions. Okay, let's start. Firstly, we have to do something that apparently looks like it has nothing to do with partial differential equations at all. If I have a certain set called omega, you can imagine in this case omega to be, for example, yeah, a set containing certain numbers, so let's say A, B, and C. Then the power set is the set of all subsets. So what does P of omega in this case mean? Well, all subsets are, for example, the sets that contain only a single value. Then we have a set containing two values, and so on. So a power set is usually something very common, the set of all sets of the set of all subsets of omega. Now, while this is pretty standard, the next term might not be so standard. The next term is called a sigma algebra. So if we have our power set P of omega, then we take a particular subset of this power set. So the big thing here around is our power set, so the set of all subsets of omega. And then we take a part of it that is a sigma algebra. And what are the requirements? Firstly, every sigma algebra on a certain set has to contain the original set omega. Then if a certain set is inside the sigma algebra, then the complement, so the whole set without that particular one, also has to be in the sigma algebra. And if I have a finite number of sets in my sigma algebra, then the complement also, then the union over all of them also has to be in the sigma algebra. I'm not going into detail here. This is a rather mathematical term. I need it for the definition in the rest. But yeah, if you want to find out more about the meaning of sigma algebras, then yeah, you can consult the literature for this. And then I need the word Borel's sigma algebra, and that is a particular sigma algebra, and the set that it is defined over, so our omega up here, is the real numbers in a certain space dimension. Okay, so instead of talking about subsets of a simple set containing A, B, and C, we are talking about sets of subsets of Rn. Okay, and while it is possible to strictly mathematically define this Borel sigma algebra, what you only need to know is that it contains almost all, let's say, important or practically useful types of sets or subsets of Rn that you can need. Every open set, every closed set, every compact set in Rn is in the Borel sigma algebra. Every interval and every product of intervals is in there too. Every set of points and finite subsets and even countably infinite subsets are in there. Why do I define this? Well, later on we want to talk about measures, which will be more or less the generalization of the term volume. And Borel's sigma algebra contains all sets where you might be tempted to define a certain volume. So you can, roughly speaking, in a rule of thumb, imagine that if you have a certain subset of your real numbers, for example, a rectangle, a weirdly shaped roundish thing, or, well, I don't know, a trapezoidal shape or something, everything where you might want to define a volume or an area in the 2D case, that is in Borel's sigma algebra. So in a sense, it just contains all those sets where you might want to define a measure or a volume. So it's only supposed to more or less exclude weird constructions where a volume simply doesn't make sense. Okay, so that's the takeaway message. Borel's sigma algebra is a set of subsets of the real numbers in dimension n that contains everything where you might want to define a volume. And now, let's talk about measures. So the abstract mathematical way of defining volume. And in general, a measure is a function defined on a sigma algebra. So here comes that again. Sigma algebras contain on an abstract set, so some general set omega, not the real numbers in particular, but maybe. On a general sigma algebra, we can define a measure, and that is something that assigns for every element in our set of subsets a non-negative real number. And it only has two requirements, and the first requirement is that the empty set has measure 0, which always makes sense if you think about measures to be the abstraction of the word volume, then it kind of makes sense that the empty set has 0 volume. And the measure for a union of disjoint sets is the same as the summation of the measures. So that's something you can easily draw. So if I have one set A1 here, and I have another set A2, and they are built such that they are disjoint, which you can see here, then, well, what's the union of those two? Well, the union is all of that here, right? And so the measure of A1 in union with A2 should be the same as the measure of A1 plus the measure of A2, so more or less the area of those two parts. So this is the mathematical way of defining a very intuitive property that we would definitely expect from something that can be seen as a volume or area measure. Okay, so on a general sigma algebra, so on a general set where I might want to define a measure, I can define a function mapping from that set into the non-negative real numbers with those two properties. And as the Borel sigma algebra was a special sigma algebra, I can also define a special measure, and that's called the Lebesgue measure, or sometimes it's also referred to as the Lebesgue-Borel measure, or sometimes just the Borel measure. It's all the same. So this is a measure defined on this Borel sigma algebra over the real numbers. So this is our set A here, and I'm missing the plus, what I've seen here. And yeah, so this is a measure, and what's important is it is the unique measure, so we can prove that there exists only one measure on the Borel sigma algebra that assigns the n-dimensional volume to an n-dimensional hypercube. Okay, that sounds like a terribly complicated definition, but actually it is quite simple. So what it only means is that if you have a rectangular shape, then your Lebesgue measure of that shape is supposed to actually give you the area of that shape in 2D. Okay? So if that's your set A, then any rectangular set A in two space dimensions can be written as a product of two intervals, right? So you would have something like A1 down here, B1, and then you would have A2 and B2 with respect to the y-axis. So it is supposed to simply reflect the term of, or the type of area that you already have in mind. And that same is supposed to also be true in 3D. So if you have in 3D a cubical shape, I'll try to draw it. It doesn't look so bad. So if you have a cubical shape in 3D, then this means you don't only have A1 and B1 and A2 and B2, but you also have A3 and B3, and then that volume is the product of all of those. So Lebesgue measure is the unique measure on the Borel sigma algebra, so on that set of subsets of Rn, that actually gives you the volume that you want. So we define it over those hypercubes, and it also, that's a fortunate thing, if you have, for example, a circle in 2D or a sphere in 3D, the Lebesgue measure of that thing is actually the area that you would expect. So for all standard geometrical objects that you can imagine, your Lebesgue measure is actually the volume or area. But it is more general, so it can also be used for different types of sets. So that's what mathematics usually tries to do. It tries to take an intuitive thing like area or volume or something and transforms it into a more abstract and general case that you can use in other ways too. Okay, so now we have a function called lambda, so the Lebesgue measure, defined on all those sets where I might want to define a volume, and it gives us this volume. Okay, and now one step further, integrals. I already said in the introduction that integrals are supposed to be the key to defining our new derivative stuff. Yeah, at this point right now, it probably all doesn't make any sense to you, because I want to define derivatives. The first thing I was speaking about was measures, so volume terminology. And now I'm speaking about integrals, and it's probably not at all clear at this point what measures have to do with integrals and what integrals and measures have to do with derivatives. But I will try to clear this up. Let's start simple. If I have a certain, let's say, area or other shape in Rn, and I integrate my one function over this shape, then this should give me the volume of A, right? So if I integrate the one function over a circle, then this integral over A of the one function is actually the area of the circle. Okay, that's something intuitive that we want. Now here comes the connection. If we say that the volume of a certain set is defined as the measure for some particular measure, but you can always think about this Lebesgue measure that I talked about. That's a bit more intuitive and better to imagine. So if we say that we define a measure to capture our intuition of volume, then the integral of the one function over a certain set should give us precisely that measure of the set. And because you can already see here that this definition hugely depends on the type of measure that you need, that's why you usually write in integral with d and then the measure that you're referring to. So that's one of those, that's more or less the other or the non-standard way of writing down an integral. So that's different from your Riemann integral that you have seen before probably, but it's a bit of a different approach. Okay, so you see here now that in an integral over a certain set, the measure that assigns volume to a certain set is a key. So here you see that this word measure and the word integral, they are closely connected. But why? So what I haven't answered to any extent at this point is the question, why do we do all of this? And if you look at what I wrote down here, then it might become a little more clear. Because if I have a set with measure 0, then no matter what function I integrate over that set, it will definitely be 0. That's something you can prove, but it's also something very intuitive, I think. So if you integrate over an area that is, or over a shape with 0 area, then of course the integral is also 0. Now here it becomes interesting slowly. So that kind of means that if you have sets with 0 measures, you can usually ignore them when integrating. And what sets do have 0 measure? And now we are restricting our considerations to the Lebesgue measure because that's the one we actually want to talk about. So now we're again talking about subsets of Rn and the Lebesgue measure. And yeah, points, so singular points always have measure 0. That kind of makes sense because they don't have an area or a volume. But then it becomes interesting because if I'm in 2D or in a higher dimension, then a line also has measure 0. That makes sense because in 2D a line doesn't have an area. If I'm in 3D, okay, this drawing is becoming terrible, I guess. So if I have a 3D domain and I want to draw a surface in here, okay, I have no idea how to draw a surface into a 3D thing, something like that. So just a surface in here. That also has measure 0. Why? Because in a three-dimensional space, we don't talk about area, we talk about volume. And the volume of a certain surface is 0. So you see that, roughly speaking, certain sets that technically have a lower dimension always have measure 0, right? Because a point is something like a 0-dimensional object because it doesn't extend in any direction. A line is a 1-dimensional object. It can be described by a single 1 parameter. So that has 0 measure if my dimension is 2 or more. Now a surface is a 2-dimensional object and that has 0 measure as soon as my dimension is more than 3. So we see a connection here. All lower dimensional objects have measure 0. What does this in practical mean, or what can we conclude from this? Imagine that I have a domain that is formed by 3 parts. My left side, omega 1, my right side, omega 2, and the boundary between those two. It's called gamma. And I want them all to be disjoint sets. So all of those 4 conditions are supposed to hold. So the union of all those 3 gives us omega, but they are all pairwise disjoint. Okay, now let's define a simple function. F of x and y is supposed to be the constant 1 if I'm in omega 1. So I have a constant 1 function here. I have a constant 1 function if I'm in omega 2. And I have the constant value 2 if I'm in gamma. So only on this straight line. That's a completely valid function. Because they are all pairwise disjoint, I can simply say that my f has value 1 in those right and left side and value 2 on the boundary between them. Now let's see what happens if I want to form an integral. If I want to integrate f with respect to the Lebesgue measure, it's important here, so I'm writing d lambda. I want to integrate my function f over the whole domain omega with respect to the lambda to the Lebesgue measure lambda. Then, of course, as usual, I can break this integral up into the integrals over the individual parts. So I have an integral over omega 1, 1 over omega 2, and 1 over gamma. And I can plug in the actual values. So on omega 1, my f is the constant 1 function. On omega 2, my f is the constant 1 function. And on gamma, I have the constant value 2. Okay, then we have seen that, well, the integral over the 1 function is always just the measure of the set. And of course, if I have an integral over the constant 2 function, then I can also take this 2 out of the integral just as usual. So I can also write this is 2 times an integral over the 1 function, right? That's obvious. Okay. So I can express all of these 3 integrals simply by the measure of their sets. And yeah, so the first one is lambda of omega 1, so the measure of omega 1, then the measure of omega 2, and then 2 times the measure of gamma. But gamma is just a line. So gamma is a one-dimensional object in two-dimensional space. This line has measure, in our case, think about it, it's area, and that area of gamma is definitely 0. So that part vanishes, and I'm left with the summation of the areas of omega 1 and omega 2. Okay, so far I haven't done anything interesting because so far I have more or less just computed the areas of those two parts omega. But now let's think about a different function f. Let's think about a different function f where I'm changing the value that I'm taking on gamma to 1000 instead of 2. And then think about you're going through the same process that I've just done. I take my function, I split the integral to an integral over all three parts, then I'm inserting my values, then here now I have inserted the value 1000, but then again it vanishes. So just as on the right hand side, here we had lambda of omega 1 plus lambda of omega 2, and here on the left hand side where we had changed f, so that's definitely a different function f, but we're getting the same result. So if I change my function values on a set of measure 0, we have no effect on the integral. Okay, now it becomes interesting. Because think about our original motivation problem. In our motivation problem, we had those individual parts of the domain, and they had a different value for this electrical permittivity epsilon, and we wanted to compute the derivative for it. And the derivative for this epsilon is no problem, so it's completely unproblematic if I'm out here in my wafer material. There I can compute epsilon. I can also compute the gradient of epsilon. I can also compute the gradient of epsilon inside of those transistors. I can also compute it inside of those conductors. The only part where it's problematic are those boundary parts here, right? That's the only part where it actually gets problematic, those boundaries between the different regions. But those boundaries between the regions are one-dimensional objects. They are just like our gamma up here, simply just lines. So if I could somehow take those advantages of my new integral which says that integrating functions over volumes of measure 0 doesn't make a difference. If I could somehow capture this observation and transfer it to my setting of derivatives, then I could suddenly compute the derivative, or the gradient in particular, of my epsilon. So maybe we can do that. So that's exactly what we want to do here now. So at this point, short recap, what have we done? We have defined the word measure as a mathematical description of our intuitive concept of volume and area. And we have observed that if we define integrals with respect to a certain measure, then changing a function on sets with measure 0 does have no effect on the integral values at all. And now our next step is to use this in order to define some type of derivative where it's completely fine if my function is problematic on a set of measure 0. So the goal for the rest of this lecture is to find out how we can define derivatives even if our function is discontinuous on sets of measure 0. Okay, now that we have already introduced the concept of measures and we have seen how we can define integrals using this concept of measure, And we also have seen that changing functions on sets with measure 0 doesn't make any difference. Now we can actually get back to where we started and get to the definition of weak derivatives and Sobolev spaces, so derivatives for functions that are not classically differentiable. First off, short interlude, the Gaussian Theorem, or as it is called in one dimension, partial integration. So if you have an integral from a to b over f times the derivative of g, then it is well known, I think they teach it in school even, it is well known that you can replace this by an integral where the derivative is on my function f and not on g anymore, and some stuff on those integral limits a and b. I think that is quite well known. So what is happening there is that you reduce the order of derivative for one function and increase it for the other, right? So we're reducing the number of derivatives on the function g and increase it on the function f. And that also changes the sign, of course. And there is something happening on the boundaries. Okay, in multiple space dimensions, this is called the theorem of Gauss. And we can do it exactly the same way. For the notation here, f is supposed to be a scalar field and g is supposed to be a vector field. But it can also be done for two scalar fields if you have, if you do it just component-wise. Let's not go into detail here. So if I have a scalar field and a vector field, and my original integral was over the whole domain omega, gradient of f times g in a scalar product here, then this can be replaced by an integral like this here. What you see here is that f is just f instead of gradient f now, so we're reducing the number of derivatives and we're increasing the number of derivatives on g. So instead of just g on the left hand side here, I have my divergence of g. And because the one is a scalar field and the other one is a vector field, in order to make it match in terms of vector dimensions, the gradient becomes a divergence. And then there is something happening on the boundary, and because instead of the 1D case where my boundary is essentially just 2 points, a and b, I now have more than just 2 points as a boundary. I have this boundary integral, and what you see here is the function f times the outer unit normal on the boundary of omega, so that's the normal vector, and in the scalar product with g. So it's essentially the same idea, but only with a slightly different boundary handling, but still we are again reducing the order of derivative for one function and we're increasing the order of derivative for the other. Okay, so that's a short interlude. And now we're getting to weak derivatives, and we start with a derivation in 1D because there it is all a lot simpler to write down, but the ideas are completely the same. Okay, assume that I have a function f that is C1, so once differentiable in a completely classical sense, so just a differentiable function on an interval AB that is open. Then I can express that integral here on the left hand side over f prime times some function psi as the stuff that is written on the right hand side. So this is just application of the partial integration theorem. So if I have a function that is C1 and I have this multiplication of the derivative of f with a function psi that is also C1, then I can simply apply partial integration. So nothing happened until here. This is just the application of the theorem on the line before. And now, if I want to put a little more restrictions into my function psi, and I'm restricting myself to the space of so-called test functions. And what are test functions? Test functions are C infinity C, so that's a complicated notation, that C down here refers to the compact support. So for any function, the support is the set where that function has values other than 0. So let's say I have a function that is constant 0 if I'm below x, and if I'm below 0, and then I go up here, and then, I don't know, I take a way down here, and then it's constant 0 again. Then my support of that function f is simply this part where f is non-zero, okay? And now, if my support of the function is compact, so closed and something else set, inside of the interval ab, then this means that if my interval ranges from a to b, then my support, and a and b, and ab is an open interval, that's also important, and my support is supposed to be compact, then it actually has to lie inside of this interval. So then my support could, for example, be a set ranging from there to there, or it's actually not the support of f, it's support of psi. Okay? So what's important here is, if I restrict myself to those functions, then the function values at both a and b are 0. And for convenience, if we want to do higher order derivatives, I also claim it, or I want it to be infinitely many times differentiable, so that higher order derivatives of psi are also well defined up to an arbitrary order. Okay, so I now, instead of taking simply a function that is once differentiable, I want a function that is infinitely many times differentiable, and what's also important, it has compact support inside of my open interval AB, meaning that I have values 0 at A and B. And what does that mean? Well, it means that if you look at this equality from up here, it becomes a little simpler, because phi of B is 0 and phi of A is 0, right? So those first two boundary terms vanish, and it means that if I do partial integration using a product function psi that is in the space of test functions, then I can drop all those boundary parts, and I can directly shift the derivative from f to psi, and the only cost is the minus up here, which I'm not getting rid of, obviously. Okay, so what we've done here is nothing special. The only thing we have done here is, if I have a function that I can differentiate, then I can apply my partial integration. And now we're going the other way around. Assume that I can apply partial integration, maybe then it kind of means that it is a derivative. What does that mean? Well, let f be a function in C of AB, and assume that there exists a function g such that this equality is true for all test functions. Okay, I see I've made a mistake here. That should not be C1, it should be C infinity. So if this equality is true for all test functions, then we can call g the weak derivative of f. Okay, why does it make sense? Well, assume that you have a function that is actually differentiable, just like before. Then obviously g is just the derivative of f, right? So g could be chosen to be simply f prime. But it's a more general concept, because we don't require differentiability. We only want, at this point, a function that is continuous. And, well, no one stops us from writing this definition, because maybe there are functions that are not differentiable, but still a function g exists such that this thing is true for all test functions. And we see that indeed this is true, because let's look at a simple example. the absolute value function is probably the go-to example for a function that is not differentiable. Why? Well, because in the point 0, so for x equals 0, down here, this function cannot be differentiated, because if I'm taking the limit from the left side, I have -1 as my value for the derivative, and if I'm taking my limit from the right side, my value for the derivative is 1. So if I'm taking this limit in both directions from here, the classical definition of the derivative, so f prime of x, the actual classical derivative, then this means that if I go from x to 0 from the left side, so with the minus here, f of x, then, okay, maybe it's not completely precise what I'm, wait, I should write it a bit differently. So let's say I'm going this way, whatever. So it's not super important. Let's drop this part, but you know what I'm talking about. So the limit from the left and right hand side are not the same. So the classical derivative is simply not defined in the point 0. Okay, and well, let's just out of the blue define a function. And what did I define here? Well, I took my function g to be -1 if I'm lower than 0, +1 if I'm bigger than 0, and simply 0 if I'm at this point x equals 0. So I just write down this definition of g. And then I try to find out what happens. Well, if I now take an arbitrary test function, okay? So psi is just some arbitrary function in my space of test functions, and I formally write down the integral from -2 to 2 of f times psi prime of x. Okay, then I can first, of course, split this whole thing up into an integral from -2 up to 0, and then an integral from 0 up to 2. So I split my integral halfways here. Then I insert the definition of f, and if I'm lower than 0, then my absolute value function is the function -x, and if I'm bigger than 0, then my absolute value function is just x. And I see here that this should not be a minus, this should be a plus. So this is just summing up two integrals, okay? Of course, because I've divided my whole integral from -2 up to 2. Doesn't matter in this case. So I have inserted the definition of f. And then I can do, then I can apply this partial integration theorem, because on every one of those integrals I can do partial integration, so I can remove this psi prime here and instead do a derivative of x, and here also remove this prime and do a derivative of x. This of course turns around the whole sign of the whole stuff, so it's minus. The boundary parts from the partial integration vanish because psi is a test function, so it's 0 at -2 and 2. And, well, what do I get? If I form the derivative of -x, of course this is -1. And if I'm forming the derivative of x, that's 1. And now, if you look at this, then I have a minus sign in the part where I'm below 0, and I have a plus sign in front of my psi where I'm in the positive part, and that's precisely, so of course this is again plus here, and this is precisely the definition of g, because g says if I'm below 0, take -1, if I'm above 0, take +1. And now, if you summarize all this, then you have the expression integral from -2 to 2 of f times psi prime, is minus the integral over g times psi. And that precisely tells you that g is the weak derivative of f. What happened here? Why does this look like magic even though it is not? Well, the important part is that in the definition of weak derivatives, we define everything only in an integrated sense. So we're only talking about equality in an integral way. So you never say that g is equal to f prime or something. You never do that. So you only say that the integral over f times psi prime is the same as an integral over g times psi. And because we have learned that the measure of that set that contains only the point 0 is 0, that thing doesn't make a difference when integrating. So in our integrals, this unique point with measure 0 just vanishes. Also interesting is if I set a completely different value in that same component of g, then you would observe that you can do that same computation again. So it's not relevant if I set the value 0 for g at x equals 0, or if I set something else. So it's simply not important, just like our example we had before with the omega 1, omega 2 and the gamma in between. So if I have those points or sets with measure 0, my values are just not relevant. And because my definition of weak derivatives only involves integrals, we can simply ignore those points. Okay, that's essentially what I just summarized already. The set that contains only the point has measure 0. It doesn't change the integral. And what's important here is I want to note that we still cannot compute the derivative pointwise at this point x equals 0. That's still not doable. It doesn't make any sense. But we have a mathematical framework now in terms of those weak derivatives that allows us to ignore it. So we observe that in an integral sense, so in the sense of our weak derivatives, it just doesn't matter that our f is not differentiable at this point. Next example. And here it becomes even more spooky. Let's see. We have the function f. It's similar to the f we had before in the first example, but if I'm bigger than 0, my absolute value function is simply shifted to the top by 1. So I have this shifted absolute value. So now that function is not even not differentiable, it's actually discontinuous. So we have a point here at 0 where we have a jump. And still, I can write down g as done here. G of x with minus 1 for x lower than 0, 0 if x equals 0, and 1 if x is bigger than 0, just like before. And that is still, you can do that computation just like before, like this one. So it's still completely fine and everything works out as before, because the derivative of that thing is the same. So now, not only are we able to compute the derivative in a weak sense for functions that are not differentiable, we don't even need continuity for this to make sense, because again, the same argument as before, our function is not globally discontinuous. It's not discontinuous everywhere. It is discontinuous at a single one point, or more precisely at a set that has measure 0. So in a sense of weak derivatives, that doesn't make any difference. So we can form some type of derivative that is independent of the fact that our function is actually discontinuous. And that's a big deal. Now let's think about our motivation again, because what did we want to do? In the beginning we had the problem that our derivative of this function epsilon for the electrical permittivity is simply not well defined, because epsilon is discontinuous, and epsilon has these jumps at those boundaries of, for example, the transistors or those conductor lines, all of those lower dimensional objects of measure 0. There we had jumps, discontinuities of epsilon. And now, if we figure out a way how to define the gradient of epsilon in a weak sense, then we are completely fine, because the weak derivative doesn't care that epsilon is discontinuous at on sets of measure 0. So with this whole concept of weak derivatives, we have found a way to make or to put sense to forming derivatives of functions that are not continuous everywhere. And the key point here, I will also summarize this again later, the key point here is that epsilon, our electrical permittivity, just like this weird absolute value function, it's not globally discontinuous. It is only discontinuous at certain small parts of the domain. And now we have created a mathematical framework to legally ignore those parts. And yeah, well, I've said that we don't need continuity for the functions to make this work, because this example that we've just seen of the shifted absolute value function is also not continuous. And what's an appropriate space for functions with weak derivatives? Actually, it's sufficient to look into a space of functions that have finite integral. Okay, so as long as I can compute the integral of a function, it's completely fine to write down my definition. And now that's the same definition as before for the weak derivative. The only difference now, f is chosen in L1, not in C anymore. So I only require my function to be integrable. And the reason why this is necessary is if the integral over f would be infinity, then this expression here on the right side would also be infinity, and then the whole thing just wouldn't make any sense. So then it's not well defined. So the only thing I need in order to make this definition of weak derivatives work is to have a function that can be integrated. And that's a very weak assumption, because that can be definitely, it can be done for a function that is, for example, like a step function here. If I form a step function like this, it's definitely integrable. The integral is just the area below this thing, and it's fine to compute a weak derivative. And what would that weak derivative be? Well, because it's a step function and constant in each one of those parts, I would have value 0 for my derivatives in all of those individual parts. And those jumping points, they simply don't matter. Okay? Now, if we go to multiple space dimensions, what would change? Actually, it's not much that's changing. Assume that you're dealing with an open set. So in 1D I had an open interval from A to B, now it's an open set in Rn, so not much of a difference. And then the L1 space is defined just like before as the space of functions mapping from omega to R, such that the integral is not infinity. And then you simply define your weak derivatives component-wise. And what does that mean? Well, if f is an L1 function, and I have this equality that I had before, only instead of a prime, I have now used dx, so the derivative with respect to the x component, then I call g my weak derivative of f in the first component. So in the sense that this gradient of f, a weak gradient, would contain g as the first component, and here I would have something else. Okay, so essentially it's the same thing in Rn, because I can do everything I did before also component-wise. Just a summary. What I'm telling you now are rules of thumb, but they can actually be proven. Of course, I'm not doing those proofs here because it's an applied lecture and it's not the contents here, but if I have a function, and that's the important part for us, if I have a function that is piecewise differentiable, for example, a piecewise polynomial function that we always get from finite element solutions, okay? Later on in FEM, we will always compute piecewise polynomial approximations to our solutions. And if that function is piecewise polynomial, then it's piecewise differentiable. Of course, a polynomial can be differentiated. Then a weak derivative exists, and that weak derivative is also defined piecewise. Okay? Just like our absolute value function, because that absolute value function is, in a sense, piecewise linear, because it's the linear function minus x if I'm below 0, and it's the linear function x if I'm above 0, right? So piecewise linear, and then I have a piecewisely defined weak derivative. And that's precisely what we'll need later. And also, of course, important to embed this concept into your classical theory. If I have a function that is classically differentiable, so just a standard C1 function, then that classical derivative is also the weak derivative. And the proof for that is pretty simple, because if you have a function that can be classically differentiated, you can simply plug it into the partial integration theorem, and you already see that this is, in a sense, a weak derivative. Okay? And a few remarks. In the following, I will use the classical differential notation, so f prime, gradient of f, divergence of f, and I will always refer to weak derivatives when I talk about this. And the reason for this is simple. If a function is classically differentiable and it actually possesses a classical gradient, then it's fine, they are the same anyways. And if not, I don't want to introduce a different notation for the weak gradient, because if I have a function that is discontinuous, of course there is no classical gradient, so I will always mean the weak gradient. Okay? So in the future, when I write gradient or divergence of f, it will always be the weak one. I usually omit writing measures to the integral, and it always implicitly means that I'm talking about the Lebesgue measure, because the Lebesgue measure lambda is the one that we have introduced to actually capture our intuitive idea of what measures should do to measure the volume. So if I don't write any measures to an integral, you can always assume that it is d lambda. And then if you want to read further about weak derivatives and Sobolev spaces and so on, I can recommend the book from Lawrence Evans about partial differential equations. It's from rather famous analysis or functional analysis professor, and this is more or less the go-to book that defines Sobolev spaces and weak derivatives more in detail. It also gives you the proofs of how those derivatives are connected to classical ones and so on, so how you can embed them in theory. That is pretty interesting. And now that I have talked about weak derivatives for quite a long time, I can finally get to the definition of the Sobolev spaces, and that's actually not very difficult anymore. So what we want to find out now is that after we have defined weak derivatives, so derivatives of possibly discontinuous function, we have to find a way to describe that those weak derivatives are, well, not too messy. So they are good enough to actually still handle them. And what we require for them is simply just that they again should be integrable. Okay? So in order to do that, we use a slightly modified integrability condition. So before I introduced L1, the space of functions that can be integrated. Now I use the space L2, that is the space of functions that can be square integrated. It's a rather straightforward proof that if I have an L2 function, then that's also an L1 function, so it's a bit more strict, this condition. Why do I consider L2 instead of L1? So L1 was more or less the minimal necessary condition that I needed in order to make this definition of the weak derivative well defined. But L2 is a bit better because L2 is a Hilbert space. Short recap, what does Hilbert space mean? Well, Hilbert space means that we have a scalar product, and that will in the future be quite helpful for us. So we can simply define the scalar product between two elements of the space, so in this case between two functions, as the integral over the product of them. And then it's straightforward to prove that if both of them are square integrable, then this is actually a finite value, so this is smaller than infinity for all f and g in L2. And you also see straightforward that the norm on that space L2 can be derived from that scalar product by simply inserting f and taking the square root. So L2 in a sense is a bit more helpful to us because it has a Hilbert space structure. In practical examples for those functions that we're dealing with, it doesn't make much of a difference. So those piecewise polynomial functions, they are always good enough. So they are L1, L2, and L whatever you want. So that's not a problem, it's just a formality. And then I give the definition for the Sobolev space of derivative order 1. And we call those Sobolev spaces the H spaces, so H1 in our case, for a certain domain omega. And that is all those square integrable functions where the weak gradient is also square integrable. Okay? So let's think about this for a second. We have seen that if f is in L2, which is a subset of L1, then we can compute the weak derivative. But technically, no one guarantees us that this weak derivative is not possibly infinity at some point. Okay? But our condition here is that those weak derivatives should be, in a sense, good enough that we can still handle them. And we captured this word good enough by saying that this weak gradient should still be square integrable. And that's all we need. So that's our definition of the space H1, and this will be the most important part in finite elements. Few remarks. Of course, you can define Sobolev spaces of higher orders HK by taking higher order weak derivatives. That can be defined in the same way. So iteratively, if I have a derivative of order 1, then I can form the derivative of that, that's order 2, and so on. So HK would mean that then I have a function that is in L2, and the weak first derivative, weak second derivative, and so on are also in L2. Of course, it is possible to define Sobolev spaces not with respect to L2, but with respect to a different LP, for example, the L1 where we started. Then we call this space WKP. So instead of just writing the K up here for the number of derivatives, we are also adding the P. So in a sense, our HK spaces, the ones that we are usually concerned with, are WK2, because the underlying integrability is the L2. And more precisely, our H1 that we usually talk about is H12. Okay? And again, just like with L2, we inherit this Hilbert space property, so all HK spaces are Hilbert spaces, and you can define scalar products on all of them. For example, the important one for us, the H1 scalar product, is the integral over the domain of the product of the two functions. So that's essentially our L2 scalar product. And then also the product of the two gradients. So that's the new part. And then you can already imagine that the iterative construction would be similar. So if you want to compute the scalar product in H2, then this would be the L2 scalar product plus this scalar product of those gradients and the second derivatives and so on. And also, of course, a derived norm that contains the part from the L2 norm here, and then something concerning weak gradients. Of course. Now, the last part that we have to talk about when talking about Sobolev spaces are boundary conditions. The reason is that in the application of partial differential equations, you sometimes want to include boundary conditions. And yeah, this is merely just a part of notation. So derived from our Sobolev space H1, so the space of square integrable functions that have square integrable first derivatives, we derive H10, and the only additional property that we need is that it is 0 on the boundary. Okay. The reason is that usually when you talk about partial differential equations, so something like I have my domain omega here, and then I want minus Laplacian of u to be equal f, and then u equals 0 on the boundary on delta omega, then you are looking for, we'll talk about this in the next lecture, then you will be looking for u in a space that already fulfills your boundary conditions. Okay, so you will be looking for u in a space that it is smooth enough and fulfills your boundary condition, but more on that later. Okay, so Dirichlet boundary conditions, where I'm assigning function values on the boundary, should already be put into these spaces. And a bit more general, that's also doable later. If my boundary is split up into two parts, one Dirichlet boundary part and one Neumann boundary part, where on the Dirichlet boundary part I'm assigning function values, so I want function values at a certain point, and Neumann boundaries assign derivatives. For example, if you imagine or if you think back at my at the heat transfer problem that I have explained in the finite difference lecture, there we had this rod, and we said that u is equal to a constant value of 100 on that left hand side here, and it should be isolated on all other parts. Then we said that gradient of u dot n is equal 0 everywhere here. Then in a sense this would be my gamma d, because here I have Dirichlet boundary parts and the rest is gamma n, so the Neumann boundary part. And then I can define a space that precisely tells me those are all those h1 functions that fulfill my boundary condition g on my Dirichlet boundary part gamma d. Okay. Not very spectacular, but the only concept that you have to take from here is that it's useful for PDE applications to include boundary conditions into your Sobolev spaces. Okay, but only the Dirichlet boundary conditions, never the Neumann boundaries, because that kind of doesn't make sense. Okay, and that's that. So let's give a quick summary of what we did today, because I think at some point it may have been a bit unclear what we want to do. We have started with a definition of the term measure as a generalization of our intuitive concept of volume. Okay, we have defined measures. Of course, before we had to define Borel sigma algebras and stuff, so sets where you can define this measure on. And then measure is a mathematical abstraction of our intuitive term volume. Using this measure, we have defined a new type of integral, the Lebesgue integral, which allows us to change integrand values, so the values of the function to be integrated, at individual points or other zero sets, without changing the value of the integral that results there. Using this definition of the new integral, which is not pointwise, but only integrated over the whole domain, we introduced a new concept of derivatives, and we called them the weak derivatives. This concept is more general and sometimes allows us differentiation of discontinuous functions, for example, if they are piecewise differentiable, as we have seen with the absolute value function. And then with this definition of weak derivatives, we have defined our function spaces called the Sobolev spaces, which contain all functions that can be weakly differentiated with a weak derivative that is still integrable. So in a sense, all those functions that can be weakly differentiated and possess a weak gradient that is good enough for our applications. Okay, so that was a lot of mathematical stuff today, and I hope you will understand most of my topics when going through this one or more times. In the assignments, we will not go into detail too much about those theoretical parts, but they are still very important in order to understand the rest. Next week, we will be talking about our problem formulation, so how we can get our partial differential equation into a form where we can use those Sobolev spaces, and that will be another slightly mathematical lecture, but I can already tell you that this one here, this lecture, was probably the most theoretical one of the whole semester. Not completely promising, but probably it is like this. Okay, then thanks for your attention, and I hope you understand the topics quite well.